I'm going to do number 18 from chapter 24. First of all, we have Gauss's law that we're going to use for this problem. And that is the electric field times the derivative of the area, and not just times, it's the dot product, equals the enclosed charge of the Gaussian surface over epsilon naught. So that's what we're going to use. So basically they're saying that we have a sphere and it has a radius of 0.4 meters, and they want to know the electric field at different points. They want it at 0 centimeters. I'm just going to say, I'm going to use it all in meters. So 0 meters, 0.1 meter, 0.4 meter, and then 0.6 meters. So what we're going to do is we're going to draw Gaussian spheres around this sphere at each of these points. And the reason that we're going to do a Gaussian sphere is because then the electric field vector will be going in the same direction as the area vector, and therefore the dot product will just be a multiplication of these two numbers, because the vectors will be parallel. The angle will be 0 in between them, and the cosine of 0 is 1. So it'll just be that times 1. So just that times that. The first one that I guess to talk about would be part A, which wants to know the electric field when R equals 0 meters. So basically just the center of the circle. If you're at the center of the circle, and they give you that they tell you that the charge is uniformly distributed throughout the volume of the sphere. So that basically means that everywhere around it, whatever's happening with the electric field around that point, it's going to be canceled out by something on the other side. So essentially, because everything is even around it, the electric field is going to be 0 at that point. The next one to talk about is at 0.1 meter. So we could draw, that's a terrible Gaussian sphere, but you get the idea. That's my Gaussian sphere at that point. So we need to find the enclosed charge. Well, in order to do that, we know that the density, which is this rho, is going to be the total charge over the total volume, which is going to be 26 times 10 to the negative 6 coulombs over 4/3 pi r, which is the radius of the sphere, which is just 0.4 cubed. I'm not going to punch it into my calculator now, I've already done that. And the value comes out to be, the value is about 9.7 times 10 to the negative 5th. That's the charge density of the sphere. So since that density is going to be the same everywhere in the sphere, because it's uniformly distributed, we can say that the charge density, which is the variable rho, we're just going to use this very thing right up here, except now we're solving for Q. We want to know what Q is when the volume is 4/3 pi, and in this case now the radius is going to be our 0.1, so 0.1 cubed. And when you do that, again, I'm not going to punch it in, but the charge comes out to be, let me see, 4.06 times 10 to the negative 7. So that's the charge inside that portion of the sphere. So now we'll go back to Gauss's law, and we know that because we have the Gaussian sphere and these things are just going to be a multiplication, E then is going to be a constant, so we can take that out, and then it'll just be an integration of the derivative of A, which is just going to be A. And I'll do that right down here. E is going to come out, and it's going to be multiplied by A And I'm not even going to integrate it. I mean, I'm just going to integrate it right off the bat. It's going to end up being 4 pi r squared. That's the area. So that's going to equal the enclosed charge divided by epsilon naught, which is 8.854 times 10 to the negative 12. And this r, we're going to plug in our r, which is 0.1 for this particular Gaussian sphere that we're doing. So if you do all that multiplication and division and everything that is involved there mathematically, you come up with the electric field being 3.64 times 10 to the 5th newtons per coulomb. And that's going to be directed radially outward, as are all of the field vectors for the sphere. So then if we want to do it at 0.4, we're basically going to use the same idea here, except that now this is just going to become 0.4. The charge is going to be the entire charge of the sphere, because 0.4 meters is the radius of the sphere. So it's going to be 26 times 10 to the negative 6. And it's still going to be epsilon naught. And now, if we do all that, then the electric field is going to equal 1.46 times 10 to the 6th. Okay. And then we're basically going to do the exact same thing for the last part, which is this little point outside the thing. I mean, we could calculate it like a normal electric charge, you know, just Coulomb's constant times the charge, you know, treat this like a point charge, really. And it would just be Coulomb's constant times the charge over the radius squared. But we could also treat it like we can make a Gaussian surface around there. And then the charge inside is still just the total charge of this charged sphere, which is 26 microcoulombs. So we can basically use the exact same thing again, but now we'll just change that to 0.6, and that'll give us the answer. So now if we do that math, punch it into the calculator, and it comes up to be about 6.5 times 10 to the 5th. And that is the problem. As I said, the direction of the electric field is going to be pointing radially outward for all of these fields. And that's it.